Hi, welcome to this video where I'm going to show you how to get the best out of your rocket design spreadsheets. So as part of the rocket briefing document, you've been given some specifications of your rocket and a problem statement, but as an engineer, how do you go about the kind of preliminary design of a rocket? And the way you do that is by writing down some physics that you know about the problem and try to understand the basic performance of the thing you're designing using these physical calculations. And you could do them on a piece of paper, but actually Excel makes a great environment for doing it because you can set things out in a nice clear way and you can implement some equations and do what-if analysis, see what happens. You could change the size of the parachute, change the amount of pressure you put in at launch and see what happens. Okay, so you've been given a link to a partially complete spreadsheet, and what I'm going to do now is show you what it looks like and take you through the process of getting it tooled up to do what you want to do. So what I have here is a completed version of the spreadsheet, and if all goes well when you download it and open it, you should start off on this first page here. And depending on how much you've used Excel in the past, just a couple of headline stuff, that we're working on a number of different tabs. So these tabs along here are different Excel sheets. But if we start here on this tab, and generally the process goes from left to right as you move along. There's some explanation here that you should read, so what it's all for. Bear in mind, this is just helping you understand how the rocket works so you can design a better one. It's not going to design a rocket for you, but it's going to help you understand things like the effect of parachute size on descent time. And to help you do this, it's been set up as a bit of a template, but just as a heads up, there's a color code here that helps you find out what's going on. So anything orange means it's a user input you've got to put in. Anything grey means it's calculated, so it's either a calculation that you've done or more likely a calculation embedded in already for you. And anything with a red triangle in the corner is a comment, so read all of those comments if you get stuck, or read them anyway. It tells you hopefully interesting things about what's going on at that part of the spreadsheet. And then the bit where you have to do the work is where these cells are pale yellow. You've got to put in your own formulas, and all these formulas are available from the briefing document, but you've got to understand what it's trying to do and how to put it in. So it's fairly straightforward, but you will have to understand how the physics works and how the spreadsheet works to do that properly. Having said that, to help you, what I've prepared is a PDF of a working spreadsheet, so it's kind of like a screenshot. So if you really get stuck and then things aren't working, I'll just show you what that looks like. So there's it's got some values on it, and it's got some example results. You can't see what's in the cells in terms of formulas, but if it just shows you that if you put in these numbers, these are the numbers you should get out, so you can use that for debugging if you need it. It doesn't give the right answer, but it tells you if what you're doing is consistent. Okay, what else we need to know? In terms of using Excel for design, one thing that's really useful is to create variable names for variables. So rather than using cell references like C7, why don't we call it atmospheric pressure or launch pressure and so on. And so in this spreadsheet I've set up a number of names of variables, and to see what they are, if you go to formulas and then name manager, it pops up this window, and what it does is it shows you all the different names. So there's quite a few things that have been put in there. So things like egg mass, and it tells you the value is 0.06 and tells you which sheet it's on, and so on. There's G minus 9.81. And so if you want to use the egg mass in your calculation, rather than typing the cell where it's in, you can just type in egg mass and off it goes. So in fact, if we try that now, if we do a cell there and we do equals and I start typing egg, so after I've typed EG it's found it, so you can click on that, and if you press tab that'll auto complete it and hit return. And so what I've done is just set that cell equal to the egg mass, so that's how we use it, and that's great, so we know what we're talking about. It's not just a random cell number and letter, it's actually given a name. Okay, something else that's really useful to be able to do is to be able to open up different tabs at the same time in the worksheet. You may not have done this before, so if you haven't done it before, this is how you do it. You go to View, you need to open up a new window, so have two windows open at the same time. And what it did there was, if I pull that down, we've now got two windows looking at the same thing. And you could just kind of put one to one side and change something and bring it back again. But actually there's a handy feature if you go to View and then Arrange All and drag that in View. And what we want is them tiled, and we want to click this one, Windows of Active Workbook. And if we do that, it puts them nicely side by side and we can see what's going on. So if we leave that one, let's put this first one on Design Inputs, and then the second one we can put on, say, Thrust Analysis for something else. So we can have both things going at the same time. Okay, so let's get into what the design inputs are and how they work. So orange are inputs, and to help you do your designing, it's much better if you ask the user to put in values that are familiar to them. So if you're asking somebody the size of a bottle, it's much easier to do it in terms of litres, because we all know kind of roughly what a 2 litre bottle looks like. But all the calculations need to be done in SI units. So what we have here is a input of 1, but just a simple formula, we calculate what that is in meters cubed. And just looking up on here, this little cell I've highlighted is the bottle volume. So if we want to use the bottle volume, there it is. So on, we've got some other things. We've got diameters of the bottle and of the nozzle itself. Parachute, so big design decision is how big your parachute's going to be. No free lunches as ever here. If you make your parachute bigger, you come down more slowly because there's more drag in principle, but the parachute is bigger, so it's heavier, and it takes longer to deploy. And you'll find that with the numerical simulation stuff. It's the deployment time which can be critical for these things. But anyway, in this spreadsheet, you'll be able to just work out if you make the parachute bigger, it'll reduce your descent rate, and you can see how that works out. Okay, we've got some masses. So bear in mind that this egg mass here is your payload. So that 60 grams there is is the payload of your vehicle, and the rest of this is just there to support the payload. Conversions over this side. We've got some aerodynamics. So the thing about the parachute is its area and its drag coefficient. And it's up to you to choose what you think is an appropriate drag coefficient for your parachute, and also a drag coefficient for your rocket. And over on this side, I've just put in if you Google drag coefficients of different shapes, you'll get loads of pictures like this. You can have a look at these shapes and what the different drag coefficients are, and you can choose what you think is an appropriate drag coefficient for your parachute and for your rocket. And bear in mind, there's no right answer. It's really you just getting a feel for what it means. So parachutes have anything between drag coefficients of 1 and 2, or even bigger sometimes, depending on the shape of the parachute. But you've got to decide when you make your own parachute, what do you think it's going to come out to. Fluid properties, fairly self-evident. Water density, air density. Environment, we've got gravity, so we're flying in a gravitational field, so that's always pulling us down. And then we get to the cool bit, which is the kind of the launch conditions. And as a designer or a launch operator, we can choose the pressure which we pump the rocket up to before release, and we can choose how much water is in the rocket. So this one, the pressure is measured in bar or atmospheres, and that's a really handy thing because everyone kind of knows what 1 atmosphere pressure is. So if we've pumped it up to 10 atmospheres, that's 10 atmospheres of pressure inside our rocket. So that's a useful thing to do. But in the analysis, we convert that to newtons per meter squared, which is a big number here, which is very hard to read. Anyway, going back to the pressure, the pump we've got will pump it up to about 15 bar, but what we found, anything more than about 10 bar and the rockets explode. So on launch day, we typically limit the launch pressure to 8 bar, so 8 atmospheres. That's still quite a lot of force inside your rocket. Water fraction, so that's how much water you put in the rocket before launch, and part of this spreadsheet will help you work out what the effect of water fraction is. So if you fill the rocket completely with water, there's no room for any air and you don't get anything at all out of it. If it doesn't have any water or very little water in it, the water comes out very, very quickly and your thrust is over so quickly that your overall impulse that you get is very low and the rocket doesn't go very far. Okay, so let's have a go at playing with this to see if we can understand what these input parameters, the effect they have on the thrust. So going over to this thrust tab now. Grey ones here, the formulas are there. The yellow ones you're going to have to work out. And just as a heads up of how this works, when you release the rocket as such at time 0, what happens is the pressure forces the water out, and in this case it's actually the water's coming out at 44 meters a second, 80 odd miles an hour, so that's pretty fast, giving a thrust of 60 newtons. But as the water comes out, you then have to subtract, or the amount of water in the rocket is decreased, and if the water volume is decreased, then the air volume must be bigger, and if the air volume is bigger, then its pressure must be lower. So as the air volume gets bigger, its pressure drops, and so then you have to then work out a new velocity. So it's now coming out at 39.5 meters a second, slightly less thrust, and then so on. You lose more water, the pressure drops, and so on. And so this is an iterative calculation. So each of these, so let's pick this value, this here. So what we've got here is the velocity is the square root of twice times F11. So that's not an unnamed sentence. So that's the pressure we've worked out here over the water density. So the velocity depends on that density, that pressure and the density of the water. When you're working out the water volume, what you need to do is start with the volume at the previous time step and then work out how much water has come out over the time step that you've just taken. So that one, the new value of the water is the old value, take away the amount of water you've lost, and that carries on all the way down here. So depending on how familiar you are with Excel, you've got to be careful how the cells reference each other. Some of these cells reference the cell above, like that one, but if you're looking at the pressure, it's actually referencing the original air volume compared to the current volume. So these dollar signs here means that it's absolute cell referencing, so it's referencing to these at the top. So it'll take you a little bit of time to work that out, but I've put in many of the formulas for you. You've just got to work out how to do the missing yellow ones. And to say all the physics and maths is in the briefing document, you've got to work out how to implement it in the spreadsheet. So what do the results look like? This is a typical chart that you'll get out. So we've got time on this axis in seconds, so that's 1 second duration, thrust up here in newtons on this axis, and on the right hand axis we've got water volume fraction. So going between 0 and the maximum value would be 1. So we're plotting that just to see the water coming out of the rocket, and then as the thrust comes down, as the water comes out, but when the water runs out, the physics is the thrust just drops to 0 pretty much straight away, because we're assuming that there's no residual thrust in the air. What we're really interested in from a rocket engineer's perspective, the area under this curve is the impulse, so that's the total momentum given to the rocket, and that's the boost phase happens pretty quick. So in this case, all the thrust is over and over after about 0.2 seconds, so a fifth of a second, it's all over. But that rocket is boosted then to its sort of launch speed, and then the rest of it is just Isaac Newton driving the rocket as it decelerates under gravity and then comes down slowly, hopefully under a parachute. So all the action happens really, really quickly at the beginning of the thrust phase. Okay, let's just have a play to see if we can understand what happens. Let's try, as if we reduce the launch pressure, so halve the launch pressure. Okay, so the amount of water stayed the same, and actually it's the thrust has lasted about the same time, but the initial thrust is much lower. What happens? Let's if we reduce the amount of water in there, the water fraction. Okay, so we've got less water, and so we get the same amount of initial thrust, but the water runs out much more quickly, and so the thrust drops off to zero much more quickly. So we're not getting the full benefit of all the energy stored in the compressed air. If we make the water fraction a bit bigger, say 0.5, we get a bit more thrust out. I should say impulse. Now we make it 0.8. So now the rocket is quite a lot of water and not much air, and in this case that the get the same initial thrust, but it drops off more slowly because it takes longer to get all the water out. So the area under this curve is possibly getting bigger, but as you can see, if we get much higher volume fractions, it's not obvious that the impulse will get higher, and if the rocket is full of water, it won't get any thrust at all. So let's just try that. So in that case, there's just a blip of thrust at the beginning, but then it drops off completely. So it looks like, depending on what your parameters are, somewhere in the middle there is going to be good for your rocket. And so you can explore how that overall impulse is affected by your choices here. Okay, so we've had a look at how the thrust is generated and how it depends on inputs. If we now look at the actual what happens in the flight, and no fancy graphics here, we've just used our equations of motion under constant acceleration, sort of thing you would have done in physics at A level, to calculate how high and how long the rocket stays up. So we've got our impulse from the thrust calculation, and we can work out what the velocity is as the impulse divided by the average mass. And then we can, from that initial velocity, we can use our SUVAT equations or whatever acronym you use for them to work out what the height will be. So basically we're firing the rocket upwards and it's decelerating under gravity, and in this case the rocket has got up to 11 meters and it took 1.5 seconds to get there. And then what we then assume is that the rocket comes down, and I've got two cases here. The first one is it comes down without a parachute, so it's just the drag of the body, and I assume it fairly quickly reaches terminal velocity and then comes down. And then the second one here is when it deploys a parachute, and once again it comes down at its terminal velocity. So interesting to see here, if we work out the terminal velocity without a parachute, it's around 10 meters a second. But if we add our parachute in, it's 1 meters a second. So by adding a parachute, we've come down a factor of 10 times more slowly. And you can see our total flight time without a parachute is about 2.7 seconds. Total time with the parachute is 11.7. So getting a parachute to come out, getting some decent height to start off with, and getting a parachute to come out is clearly important here. Let's see what happens if we increase the launch pressure. So with the parachute, time was about 12 seconds, so let's go up to 10 bar. So we've doubled the pressure, and actually our flight time is now closer to 30 seconds. So obviously we're getting a higher launch and it's coming down more slowly. So 30 seconds is pretty good. The record we've ever had for a student rocket was about 37 seconds, which is pretty amazing. Most rockets are lucky if you stay up more than 10 seconds. But if you can get a really clean rocket that gets a good height and gets to deploy a parachute right at the top, you can stay up for an awfully long time. Okay, what I did here, just for my own benefit, I did a quick experiment where I varied the water volume fraction, and then I ran it, and then I just typed in the values here I got from the table opposite of how long it stayed up, and I plotted these. So just to see what happens as you vary the water fraction and what happens to the flight time. So clearly the one with the parachute stays up much longer, but both of them have some sort of optimal value somewhere in the middle. Interesting little kink in there. That's not an error, there is a kink in there. No idea where that happens. There's something slightly funny in the physics that makes that happen. But as a designer, you would look at this and say, okay, there's some sort of optimal water fraction. It's somewhere in the middle there. So it's not going to be 0, it's not going to be 1, somewhere in the middle, and that would guide you in terms of what choices to make. Okay, so that's a quick whiz through how the spreadsheet works. And just to remind you, the purpose of this isn't to get a right answer or even to design your rocket. The purpose of this is for you to understand how the design parameters vary the outcomes of your rocket. And what this does is it gives you engineering intuition, so when you're making decisions about how to do things, you can make good choices. So things like launch pressure, you don't have a lot of control over. The rocket's going to explode anything much above a launch pressure of 10. But things like drag and things like mass do make a difference, and you can control that. So when you're slapping on extra layers of tape, or you're putting on a very heavy nose cone or the like, you can think, actually, what difference is that going to make? Okay, and then the last thing to mention here is that when you're doing design, you usually use a number of different tools at different phases. So this is your kind of first quick look using basic equations of physics, essentially A-level physics, applying to this, and it gets you an answer quickly to see what happens. But there's many things that we can't simulate in this. So for example, just one comes to mind is that the parachute just comes out. We assume it comes out immediately, but in real life, to deploy a parachute, it takes a finite time. And so the bigger your parachute, the longer it will take to come out. So things like changing parachute size is not just as simple as make it bigger, you stay up longer. At some point, you're going to actually stay up shorter because your parachute's not going to come out. The other things which you'd be interested in are the proper aerodynamics of the rocket. So on the way up, there's a lot of issues with stability. So does it actually point in the right direction? So if there's a crosswind, what does it do in that? And if you're at the top of launch, how do you actually get the nose cone to come off? So it's all very well having a parachute, but actually it's really quite tricky knowing when the parachute comes off on and off. So those things we can't answer in a spreadsheet, but for that we develop a more detailed numerical simulation, and that's what the Unity simulation work you'll do later is for. So I hope you enjoy using the spreadsheet. As I use it to guide your spidey sense for how to design rockets, and then so when you're in the lab making things, you can refer back to this and understand, okay, we're going to make it like this because these things are important. Okay, hope you enjoy using the spreadsheet.